Hello, Internet. As you can see here, this is where we want to apply now sentence transformers to. It is an interplay of natural science, social science, and economic science. And it is interesting because we want to have a view if we apply sentence transformers. Can we have an understanding of the interdependencies of climate, biodiversity, and people? So let's jump right into this. And at first, we need data. For sentence transformers, it's easy. We need sentences. To get sentences, I have chosen here as a demonstration object the 3,675 pages of the latest IPCC report. So 3,600 pages are quite enough to have a complicated interplay between disciplines. What we do then? Now, the next step is that we take a sentence embedding, SBERT as a model. And if you look at the instruction, you have a particular chapter on clustering. And we're gonna use exactly this clustering with sentence transformers to have a look at a visualization. Now, after the sentence embedding in a 768-dimensional topological space, we have to reduce the dimensions. I will do this. I will show you with UMAP, and here you have the UMAP API guide. And as you can see here with UMAP, we have quite a lot of let's call it parameters to adapt to. UMAP, if you're not familiar with this, maybe you know TSNet, is a uniform manifold approximation and projection. It's a beautiful piece of software, and it finds a low-dimensional embedding of the data. This would be our sentences of more than 3,600 pages that approximate the underlying manifold structure. You will see that we will play around with the number of neighbors. I have it at about 50, the number of components, this is the dimensionality, you want to reduce it. I will have a reduction from 768 dimensions to about 50 dimensions. You can choose your Euclidean metric, your cosine metric, your specific metric for your data. You can choose the output metric, and you have a negative sample rate. We are familiar with this. Some random state, categorical target metric. It is a huge amount where you can do some fine-tuning. And after we reduce this manifold approximation, the next step is to have a cluster algorithms. And we have here a particular form. It's a clustering from a vector array. And you will see that here also a lot of parameters we will optimize. The cluster size, for example, I will have 500. So 500 sentences is the minimum cluster size. Or if we want to have a lot of clusters in our visualization, you can decrease the cluster size. The minimum sample size tells you a lot about the topological neighborhood that you want to have analyzed. I will show you the different values. Then you have Euclidean metrics, cluster selection methods. I have leaf for examples, but it's totally up to you. For the network structure, for the network analysis, and I will use Python only, I rely on Network X. It's a Python package for creation structure dynamics of complex networks. So if we have the cluster in a low-dimensional space, we will use Network X. And finally, the last step is I will use Plotly. Plotly for Python. Plotly for Python is free. It's an open source software. It costs nothing to install and use. GitHub repository. I want to do this without any costs involved. And I want to show you where are we if we apply these steps of Python software packages. If we go through this, then we will try to understand the system. You can see here a visualization from our satellites from NASA, by the way, provided by NASA. Thank you, NASA. And then the report. The report tries to summarize this ecosystem biodiversity and human communities at a global level. We will use these sentences, but our main topic is, can we understand the complexity, the interplay of the different systems with sentence transformers, and how do we apply sentence transformers to reach our goal? Where we will end is, and let me show this in the next video. Just a short interrupt. This is my Jupyter notebook. Let me have a look. I'm going for the cluster algorithm. And here, for example, you can see here the cluster of my sentences. And I use here the HDBSCAN minimal cluster size of 550. I use a minimum sample size of 5. And then more or less, this is the command. You have HDBSCAN, minimal cluster size, the metric, I choose Euclidean, the different CPU cores you want to have, the minimal sample size, your epsilon, your methodology, I chose leaf, the algorithms, and whatsoever. And of course, you apply this to your embeddings. And what you get is a cluster identification label. So you have, where is it? Cluster 2D. No, we want to make it in 3D. That if you have this cluster, you will get a cluster label for each and every sentence of all of the 3,600 pages. And then we will go on and have an implementation. Yeah, with subcluster, I'm going to show you in a minute. Both clusters, multiple cluster, topological cuts over clusters. No, let's go with the visualization. Hold on a sec. And so, as you can see here, this is the result of our compute. We have here in a three-dimensional visualization all our sentences. And what I did is I optimized the UMAP topological embedding, the reduction of it, and the cluster parameters in a way that you can see here 29 clusters. And those 29 clusters have now an interesting topological shape. But of course, since we use a cluster algorithm that does not allocate each sentence into a cluster, but I have chosen a particular core cluster functionality, we can just switch off the noise in this cluster, multiple cluster visualization, and have a more detailed look at this. Just let me bring it up to you. Let's dive into this. And if you now look around, you can see here that the BERT model, our sentence BERT embedding, our machine learning, where we use the pre-trained BERT model from Hugging Face, because I do not have the time to train this for, I don't know, 100 or 1,000 hours on an A100. This is from a pre-trained model, sentence embedding model, and let's have a look at the cluster distribution. So what I want to show you here is, I don't know, let's start with a simple example. Let's take something like food security. Oops, where are you? Here you are. This is our cluster about food security, the global food, anything related, hundreds and thousands of sentences about food. And then I want to see the crop production. So we activate now cluster crop production. And as you can see, this is really close by. So the distance in this vector space, and this topological vector space, of course, tells us something about the intercorrelation of these two topics: food, crop production, yield losses, crop yield. And then, if you want, you can switch on some other topic. What about, I don't know, extreme event, climate change, uncertainty, taken soil moisture. Why not soil moisture? Oh, it is a little bit more over there. You might ask, hey, is there an interlink between those? I don't know. Let's have urban heat is not city. No, we don't want to have city right now. Woody plants. Let's have a look at this one. Oh yeah, this is interesting because suddenly we have a bridge between them. And there's a topic called woody plants, woody encroachment, semi-arid climate zones. Now, what else we have? Let's have a look at no ocean. I don't want to do ocean right now. Wild bank, no. Indigenous people, no. A little bit later. Fishery, a little bit later. Tropical forest. How far are tropical forests away? Oops. Where are we now? What happened with tropical forest? Let me have a look. Oh, this is just over there. So, just to give you an idea, if you have just 29 clusters, you can already see here that the interplay between, in blue we had food security, then crop production here in this pink, and in green we had soil moisture and semi-arid climate zones. You can see that they clearly have a relation, and what you would expect from your normal understanding of ecosystems. Also, our sentence embedding visualization was able to map this accordingly. So if we switch on now everything again, hold on a sec. To switch on everything again, I have a little notebook and it takes a little bit of time. Here we go. No, yeah, University Press, I can delete University Press. You see that the cluster distribution from just 29 clusters that our sentence embedding produced with a pre-trained BERT model is already quite interesting. And of course, now you say, let's go the next step. And the next step, I used a little bit more time. Now it's about 1 hour code processing time on a free Colab. We have now 56 clusters. And as you can see, now you have a much finer granulation of the topics. So let's dive right into it. And we have a similar structure. It depends, of course, on a lot of parameters in UMAP and about the cluster algorithm, how dense your algorithm will calculate your cluster size. You can play around with this. I spent about 6 hours for this presentation to optimize it in a way that I think is okay if I can show you here on YouTube. But the more time you invest, the better it gets, of course. What else? Let's focus about water. What about water scarcity? And I want to have water as my primary topic. Okay, takes a little bit of time. Here we go. So these are all the sentences correlated in this particular cluster with water. Let's focus a little bit. Get into. Okay, this is my water cluster. All the sentences here in the water cluster. And what I will show you, of course, you can take this cluster and apply a further subclustering, and then you will get all the details concerning water. But we can apply an even more intelligent solution. Let me show you. Next cluster was going to be about flooding. So water scarcity and flood risks. And you see, okay, yeah, there's a little bridge there. So this is not enough water. This is much too much water, flooding. And then you can ask, okay, what's living here? What's living in this area surrounding this? And this is just a very simple 3D visualization, as you can see. But you can play around with this quite easily to understand the missing elements that I don't understand in those interplay of ecosystem. So let's say extreme events. Are we there close by? Yeah, of course, each cluster generates a new visualization. It's a little bit strange. Okay. So here now in this ochre, we have our warming events, our extreme events. What else can we have with water? Let me have a look. South America. Tropical forests. Where are tropical forests located? See, I don't see them. Tropical forest in pink. Oh yeah, they're over there. And then, ocean. Here we go. Acidification of oceans. You know something? I take away the tropical forest to focus a little bit about ocean. Then we have sea level in blue over there. Let's focus a little bit into, that we can have a look at this in more detail. And sea level rise, we activate sea level rise, of course, interconnected. So you can see the further you go into, the higher your amount of clusters are, the more interesting your topological presentation becomes. You can have add the fisheries in dark blue, and that's interesting. You will see outliers, but remember that the clustering has been calculated not in 3D, but in my case, close to 50-dimensional space. So whatever you think is an outlier in a 3D space might not be an outlier in the 50-dimensional space that was calculated. But I guess you get the idea. No? Dark blue is fishery, contains everything about water. Interdependencies, you can indicate now the size or whatever. So this is the middle ground with 56. If we go crazy and we say, okay, let's spend 2 hours on Colab, just compute time, we get about 83 clusters. And those are my 83 clusters, and you might say, heaven's sake. So this is the complexity I want to show you. And this is now here what we see if we do a sentence embedding of our 3600 pages. And we have a cluster size close to 100, 83 exactly. And now you can dive in. You have now, for example, permafrost, you have sea ice, you have the polar region, you have the Antarctic Peninsula as subclusters. So you can dive into this. You can see the semantic distance, how the interconnect, how the interplay takes place between the different elements in those ecosystems. This is it more or less for today, but what I want to show you, how I do this. Let's say sea ice. Give me a sec. And I take the Antarctic Peninsula and permafrost. Yeah, my little notebook takes a little bit of time. It was too much for it. Hello, we're back. Sea ice. Sea ice, permafrost, glaciers, permafrost. So, here we have what you think would belong also quite nicely together. So let's go. The orange one is glacier, the red one is permafrost, the ochre one is polar regions, and the blue one is the Antarctic Peninsula. Now, if you say, okay, these are my 4 areas of interest that I want to have a deep dive into, you can also use sentence transformers, because what you can do is, for example, you can define this as the set of sentences. I don't know how many thousand sentences are hiding behind this visualization. But you can say, okay, this is now my new starter set. These are my data. This is the data I selected. And now you do the same. You do the embedding of those sentences in a new vector space. You do UMAP, you do the clustering, you do the visualization. And I have taken 2 clusters, and I've chosen, it was not exactly particular these 2 clusters, but just to give you an idea. And I said, okay, I just want to have a deep dive into these 2 particular cluster I have chosen from the report without reading all 3600 pages. How can I deep dive? Would the result be sensitive in any way? And I used this calculation. This is now close to 5 hours on every collab. And of course, as you see, I increased a little bit the accuracy of our sentence transformer calculation. This is it in 3D. You can deep dive, you can have a look at all the different sentences if you want to know what's going on in a particular surrounding. And then I've chosen 2 clusters. And if you have 2 clusters chosen and you do a sub-analysis, so in our old picture, this would just be red and this would just be blue. But if you again apply sentence transformers in detail, you will see that you get this further subclustering. And what you see here, I don't know if you can read it, we have now water sanitation hygiene, we have desalination of seawater, we have water temperature, we have deep water, we have the water use, we have terrestrial fresh water. Maybe we click on this one. Yeah, but I want to have this one. Should have switched to another computer. Come on, thank you. So we have terrestrial ecosystem and terrestrial fresh water. And as you can see, they are clearly correlated. What else we have? We have water management in urban areas. No, not for the moment. And we have water security. Let's add on water security. Oh, water scarcity. Okay, over there. Water availability, okay, is in this cluster. So you can see that here more or less you have the freshwater cluster, and here you have the security water scarcity cluster, the water availability cluster. So you can even fine-tune your sentence transformer to get this topological vector space representation, even if you choose a particular topic. And I think it's really nice what you can do with sentence transformers if you want to analyze some complex interplay between, as I told you, the interdependencies of climate, biodiversity, and people. And yeah, it is also about the critical infrastructure, you know, the water, clean water, water scarcity, electricity, all transportation, food, health, all the cotton fields, the wheat fields. How would they suffer if suddenly there was not enough water available? What about all the pesticides you use to turbocharge the growth? What about genetic modified particles? It is really fascinating to have some visual understanding of a really complex content. And I hope I've given you a glance, an idea what you can do with sentence embedding, with sentence transformers. But of course, a clustering is not enough. We need an interactive component, some edges, some links, some interplay between the different cluster elements. And I think this will be a graph theory, maybe a graph embedding, a graph neural network application in the next video.